Geometry students, there is a lot of information in this video, 2 lessons again, but I trust you. I think you can do it. So let's take a look. We're going to start with a new definition. An inscribed angle is an angle whose vertex is on the circle and whose sides contain chords. The arc that lies in the interior of an inscribed angle and has endpoints on the angle is called the intercepted arc. Good? Some language. Interesting theorem. The measure of an inscribed angle is half the measure of the arc. So the measure of the arc is the measure of the central angle. And the measure of the inscribed angle is half this central angle, half the intercepted arc. Let's take a look at the proof. The proof involves a couple different cases. So I'm just going to talk about this first case. Do you see this isosceles triangle because of those two radii? So I know this angle is the same as this. Well, now I know that this angle is twice that because it's x plus x. It's an exterior angle. So if this is x plus x, that means this is 2x where this was x. Something similar here, you just draw a diameter there, and you can get the same isosceles triangle here. You can get a different isosceles triangle there. Good. This angle right here is this plus this. This angle right here, this angle right here is this plus this. The first angle is that plus that. This whole angle ends up being this plus this plus this plus this. There we go. The last one, you have to do, I think, the same thing, but now it's like you do like a little minus situation. Good. So you've got an isosceles triangle there. Good. And you've got here, that one's hard. I'm going to have to look at that one again. I don't know how that one's going to work. But these have to deal with isosceles triangles. Here, I think I might have to do a little angle addition or arc addition postulate that this arc is this plus this. And then I've got this here. So, yeah, I think I could do it, but not as cleanly as I did the others. You don't have to prove it right now. You just need to know that the measure of the inscribed angle is half the measure of the intercepted arc. From that one theorem, we get a lot of different other theorems. We can prove that if two inscribed angles intercept the same arc, then they're congruent. That one's pretty obvious. We can start talking about polygons that are inscribed in a triangle, or we can talk about circles that are circumscribed about that polygon. And then once we get a polygon inscribed into a circle, we've got 1, 2, 3, 4. We've got all these different types of inscribed angles as well. So we start to look at if we have a right triangle in a circle, what does that mean? Well, it can only be a right triangle if we know that this is a semicircle because twice 90 is 180, so there's your 90-degree angle, right? And so all this one says is that if a right triangle is inscribed in a circle, then the hypotenuse is a diameter. And the converse is also true, that if one side of an inscribed triangle is a diameter, then that triangle has to be a right triangle. And you end up getting this, you know this inscribed angle is 90 if and only if that side there is a diameter. Another useful theorem talking about quadrilateral. If I look at angle F, I'm going to extend the sides of angle F. Do you see that angle F inscribes arc EDG? And then if I use a different color and I look at angle D, do you see that angle D intercepts arc EFG? Now, I don't know what angle D is and I don't know what angle F is. But I know that angle D inscribes part of the circle, and angle F inscribes all the other part of the circle. So I know that the measure of angle D plus the measure of angle F equals 1/2 the measure of all of these arcs. Now, what do all of these arcs add up to? 360. So I get that the opposite angles in an inscribed quadrilateral are supplementary. I'm not saying each is 90. I'm just saying that the opposite angles are supplementary. So angle D and angle F are supplementary if that quadrilateral is inscribed in a circle. So that's one lesson. If we go back, that's 8.4. It's really built on this idea that an inscribed angle is half the measure of the intercepted arc. Everything else flows from that. The next unit talks about, well, what if you've got a tangent line and a chord? And it's kind of similar. Even though we can't call it an inscribed angle, it's a similar idea. Notice that arc ACB here and angle BA, let's call this E, angle BAE or angle 2, it's half of that arc, and that's like an inscribed angle. It's not, but its vertex is on the circle, and it intercepts an arc, so that angle is half that arc. Same with angle 1. And, it also fits that we know 1 and 2 are a linear pair, so we know they add up to 180, and this entire circle is 360, so we're getting that kind of half relationship again. This also plays out with some other things in a circle. So right now we've got a secant line and a tangent line and how those create angles. Look what happens here with a couple of secant lines. This can also work with tangent lines, so we can have the secant lines, not tangent lines inside, but the secant lines can intercept on the circle, inside the circle, or out of the circle, and we get some interesting theorems when they're inside the circle. Looks really complicated, but I'll just explain the basic idea. We know angle 1 is congruent to angle 3. We know angle 2 is congruent to angle 4. But what we don't know is we don't know if this is the center of the circle. If this was the center of the circle, this would equal the measure of arc AD, but it's not the center necessarily. If it's not the center, you can use this theorem that says the measure of angle 1 is half the sum of arc DC and half the sum of arc AB. So you have to take both of those arcs, add them up, and then divide by 2. It's the average of those two arcs. And angle 3 over here would be congruent to it because they're vertical angles. 2 has the same thing, except now it's arc AD and arc BC. So you take vertical angles inside the circle, and you look at the arcs they intercept. Good? We get a different but similar theorem when we have them outside the circle. If we have two secant lines, let me go back to that. If we have two secant lines, you take this arc, but now since it's outside the circle, you subtract this arc. You take the difference of those arcs, divide by 2, and you get the angle. You take the difference of these two arcs, divide by 2, you get that angle. You take the difference of those two arcs, divide by 2, and you get that angle. I'm not going to pretend that these two theorems are easy. Like, oh, duh, that's obvious. But once you have them written down and you're looking at them, it's not hard to apply. They're easy theorems to apply, but they may not be easy theorems to think of. It's a really great thing that you have a yellow book where you could write down all the theorems that you might want for the final exam. Just something to think about. So we've got all of these theorems here. Now that's it for unit 10.5. So again, I'm doing 2 units tonight. It's a lot of information, but I don't think the information's tough. Write down your theorems. Write down the theorem that an inscribed angle is half the intercepted arc. Write down that inscribed angles that intercept the same arc are congruent. Write down the theorem about right triangles and semicircles. Write down the theorem about opposite angles of an inscribed quadrilateral being supplementary. Write down the theorem about a tangent line and a secant line intersecting at the point of tangency and what that means for the angles. Write down the theorem about 2 secant lines that intersect on the inside of a circle and how do you find angles, and what happens if you have a tangent and a secant, 2 tangents or 2 secant lines intersecting outside the circle. That's a lot of vocab, it's a lot of theorems, but I hope it's not too tough. Have a good night. Peace.